So to derive our equation for calculating how the gravitational potential energy is going to change as we move one point mass relative to another, let's start with a couple of point masses here. So I'll have mass 1 and mass 2. So of course I recognize that the gravitational force wants to pull these masses together. And so I'm going to choose to move mass 2 opposite the way that the gravitational force is trying to pull them. So when I go to calculate that out, I know that the change in the gravitational potential energy is equal to negative the integral from some initial to final position of the gravitational force dotted in with my infinitesimal little displacements. Because dr points to the right and the gravitational force vector points back to the left, that dot product is going to give me a negative. That negative is going to cancel the one sitting out front. I can also bring out g mass 1 and mass 2 because they're just constants. And so I'm left with the integral from some initial to final position of 1 over r squared dr. Well, when I integrate that, I still get my g m1 m2 out front. And this integral is going to give me negative 1 over r that I need to evaluate at the endpoints. And so I'll just pull the minus sign out front. And when I evaluate this, I'm left with the change in the gravitational potential energy equals negative big G times the product of your masses times this term in parentheses 1 over RF minus 1 over RI. So let's be clear about what those R's are. RI is the initial distance between your masses. RF is the final distance between your masses. So in this expression, RF and RI are always positive. So these two distances are always positive quantities. So if our two R's are always positive, G is a positive constant, our two masses are always positive, then we can figure out whether or not the gravitational potential energy is increasing or decreasing by thinking about what's going on with the subtraction inside this parentheses and whether or not that cancels out this minus sign that's sitting out in front. So if I move my masses towards each other, then the initial distance separating my masses is greater than the final distance separating my masses. But of course that means that 1 over r final minus 1 over r initial is a positive thing. I took 1 over the smaller thing minus 1 over the larger thing, and that ends up being positive. If the term inside my parentheses is positive, times positive g times positive mass, there's nothing left to cancel that minus sign, and so that tells me that the gravitational potential energy will decrease. That's consistent with what we talked about in the previous video, which is in letting my masses come together, their gravitational potential energy will decrease because they're moving with the gravitational force. The gravitational force wants to pull them together, and so in letting them come together, they're moving with the gravitational force, and the gravitational potential energy decreases. On the other hand, if I move them away from each other, so now the final distance is greater than the initial distance, which means 1 over r final minus 1 over r initial is negative. Negative term inside my parentheses cancels that minus side out front, and I get that the gravitational potential energy increases. So pulling your masses apart increases the potential energy, and again that makes sense because I know that in pulling them apart I'm moving against the gravitational force that was trying to pull them together. So as with any potential energy, what we will often do is want to talk about the gravitational potential energy. And of course, to talk about the gravitational potential energy, what we really mean is the gravitational potential energy relative to the point where the gravitational potential energy equals 0. Never say it, always mean it. So we must have a 0 point if we want to talk about the gravitational potential energy. Well, in this case, given our expression, what we always do is set the gravitational potential energy to be 0 when our masses are infinitely far apart. We can rewrite our equation so that we get that the gravitational potential energy for a set of point masses is given by negative big G m1 times m2 over r12, where r12 is some finite distance between the masses, because I know if they're infinitely far apart, then ug is going to be 0. One of the things to highlight, G, M1, M2, and R12, those are all positive quantities. So this minus sign sitting out here in front tells us that the gravitational potential energy when we're dealing with point masses is never positive. So if we were to plot this out, and so you'd have increasing gravitational potential energy versus increasing distance between my masses. Well, as my masses get close together, I actually have a very large negative value for the gravitational potential energy. But as I move them apart, again, I'm increasing that gravitational potential energy and moving them apart, but I never get to the point where I actually get a positive value. I'm increasing the gravitational potential energy by going to less and less negative values for UG. And again, the only way I actually get to zero is getting my two masses infinitely far apart. So some important points to think about in terms of using this equation to calculate out the gravitational potential energy due to point masses. 1, the gravitational potential energy is never positive. The change in the gravitational potential energy can be, but the gravitational potential energy is never positively valued. It's negative for finite distances. It's zero when your masses are infinitely far apart. 2, increasing the gravitational potential energy means that the value of UG is becoming less negative. It's getting closer to zero, but it's still always negative. 3, gravitational potential energy depends on two masses, like the gravitational force. But unlike the gravitational force, it's a scalar, not a vector. And we'll see why that's a good development in a second. 5, R12 is defined to be a positive distance. So don't make the mistake of trying to plug this in as a component where it could be negative depending on some choice you might make in coordinate system. This is defined to be a positive distance. And then 6, that the gravitational potential energy goes like 1 over r, not 1 over r squared. Gravitational force was 1 over r squared. Gravitational potential energy, 1 over r. Now, if we've got multiple masses, and so we want to calculate the gravitational potential energy of one mass in the presence of multiple other point masses, well, again, what we need to do is just calculate the potential energy due to each interaction and then add them up. The nice thing here, of course, is that the adding them up is so much easier because the gravitational potential energy is a scalar. So if I want to think about the gravitational potential energy of mass 1, and again, that's really the gravitational potential energy of mass 1 relative to the point where it's infinitely far away from these other masses, where the gravitational potential energy would equal 0, there's two interactions between mass 1 and mass 2 and between mass 1 and mass 3. So I have two terms here that I need to calculate out. I'm going to use my equation, negative g product of masses over distance between them. I just get to do it twice. Once for the interaction between mass 1 and mass 2, once for the interaction between mass 1 and mass 3. On the other hand, if I want to talk about the gravitational potential energy of a system of multiple point masses, so not the gravitational potential energy of a single mass, but now the gravitational potential energy of this entire system. Well, now I need to think about all the possible interactions, and we had two of them between mass 1 and mass 2 and mass 1 and mass 3. We just need to add in the third. And so there's also an interaction between mass 2 and mass 3. And so there are three terms here, and again, we calculate out each term by negative g, product of masses involved, divided by the distance between them. What this term is equal to is the work required to build your system of masses. So whatever the gravitational potential energy is stored for your full system is another way of saying how much work was required to put that system together.